So in this question here, we've got an initial value problem. We've got y double prime plus y equals t minus 3 times sine of 2t. And the initial values are y at 0 is 1 and the derivative at 0 is minus 3. So how are we going to go about solving this, trying to find our y? So it looks like y is going to be a function of t. So that's our goal. We need to find y of t. Now there's a couple of ways we can go about this. Today the technique I'm going to use is the Laplace transform method. So what I'll do is I'll take the Laplace transform of all of these and turn it into some value with the variable s, and then we try and solve it and try and get an answer for y is t by doing the inverse transform of our solution. Okay, so first of all I need to do the Laplace transform of all of these terms. So I need the Laplace transform of y double prime plus y, so that will just stay as it is, so Laplace of y, and then we need the Laplace transform of t, so the Laplace transform of t minus the Laplace transform of all of that, so the Laplace transform 3 sine 2t. Okay, right. Now if you check the link below, you'll see some videos on how we created the Laplace transforms of all of these using integration. So I'm going to go straight in with the results, and if you want to see how they're obtained, you can check the links below in the description. So y double prime, the Laplace transform of that just becomes s, so I'll start over here to give me a bit of space, s squared Laplace transform of y, and after that we've got minus y prime at 0, so we've got that value there, and then we subtract s times the value at 0. So this just represents that. Now the Laplace transform of y, I'm just going to leave that as it is. So add the Laplace of y. Okay, now we need the Laplace transform of the variable t. Now if I take any variable, the Laplace transform of kt, that just becomes k over s squared. Okay, so I can plug that into there. So here my k is just 1, so that just becomes 1 over s squared. And this one here, the Laplace transform of that one, so if I have the Laplace transform of k times sine at, so here k is 3 and my a would be 2, that gives me k times a over s squared plus a squared. So that takes care of that one. Okay, right. Now with this one here, k would be 3 and a would be 2. So I'll have 3 times 2, which would be 6. And my denominator would be s squared plus a squared, which is 4. So it's s squared plus 4. Okay, right. That's everything to the Laplace transform. Now what I can do is I need to try and do something on this side to get my s variables on their own like they are on here. So if I factor out the Laplace of y, so Laplace transform of y, and then the variables that we have with that is s squared, and this one here, well there's just one Laplace of y, so I can just put plus 1. Okay, here I can put my values that I have, which is y prime at 0, so that's minus 3. So minus 3, that just becomes plus 3. And minus s y at 0, y at 0 is 1, so that just becomes minus s. Okay, so I've put that in a bracket, and that equals 1 over, now if I've got s squared and s squared plus 4, why don't I try and get a common denominator and write this as s squared plus 4, and then what I would do is just correct these numerators by multiplying by the appropriate term. So here, to get this one, I'll have to multiply this by s squared plus 4. So this now just becomes s squared plus 4. and then subtract. This 6 we'll have to multiply by s squared, so that's minus 6s squared. So that takes care of that. Right, now let's get this term over to this side. So this, I'm just going to put an arrow, that's just going to bring down. So give myself a bit of space and start over here, as I'm going to bring this one over. I'll just rewrite this term here. So I've got s squared plus 4 minus 6s squared plus 3 minus s. I'll leave that as it is like that. And my denominator for this will still stand s squared plus 4. Okay, right. This 3 minus s, be good if we could just include this inside this denominator here. So what I want to do is write this as that. So s squared plus 4. And now I'm going to need to put that multiplied by this term as well, otherwise I've changed the value. So s squared plus 4. Okay, right. Let's see if we can simplify this off even more. Now here we've got an s squared plus 4 minus 6s squared. So I can rewrite that as minus 5s squared and a plus 4. So I'm going to write 4 minus 5s squared. I can leave that in a bracket. That'll take care of all of that. And then here plus 3 minus s squared plus 4. That takes care of all of that. So I'm not going to FOIL that one out. And my common denominator will stay. I've now got s squared plus 4. So that takes care of this side. I'm going to leave that as it is. Now here, I want to get Laplace of y on its own. So if I divide both sides by s squared plus 1, I'll isolate the Laplace of y. So now, if I divide both sides, I just need to put an s squared plus 1 on this side. Okay, right. Now, what I need to do now is perform partial fraction decomposition of this to separate it all apart. So, if you check the link below, you'll see a video on how we did the partial fractions, because it's quite a complicated process and quite an interesting way to see how I did it. So if you check that, and you'll see what the result was. So I can just now write the result in there for us. So now I've got Laplace transform of y. That gave us 1 over s squared. So that was that term. Now the s squared plus 4 term, that was just a 2. So 2 over s squared plus 4. So make sure my s's don't look like 5s. And then I had s minus 6 for my s squared plus 1 term. So plus s minus 6 over s squared plus 1. And that was the partial fraction decomposition taken care of for this. Okay, so now I need to make some space. So I'm going to clear some of this off the board, and then we're going to try and do the inverse Laplace of these terms here. Okay, so that's where we're up to. So now to get y on its own, I need to do the inverse Laplace of all of these terms. So inverse Laplace of 1 over s squared. Then this one here, the inverse Laplace of 2 over s squared plus 4. That takes care of that one. And then this one here, so add the inverse Laplace of s minus 6 over s squared plus 1. Okay, well, this one we already know. So this one, 1 over s squared, that was the reverse of this one. So here our k is 1. So basically it's just the Laplace of t, just gave me t. So that's that one. So y, we write it as a function of t as it was before. So therefore our variable here would just be t. Oh, so this one here, I'll take the inverse Laplace of that one. I will have k would be 1 because my a squared would be 4. So therefore a would be 2. So therefore I would have sine of 2t. So that's take care of that one. Plus sine of 2t. So that's good. And then this one here, now there's not a direct inverse Laplace of that one just yet. So what I'm going to do is I'm going to break the fraction apart and see what we get. So now let's just break this apart. So just write the s over s squared plus 1, and then minus 6 over s squared plus 1. Okay, well this one looks a little bit similar to what we could have here. So I've got plus 1, so I need a 1 in my numerator here, and then the minus 6 I could bring out as a multiple. So I could have minus 6 times 1 over s squared plus 1. Well, s squared plus 1 using this method here would be just sine of t. And then I've got a minus 6 multiplied it, so I could start off having minus 6 sine t. So minus 6 sine t. So that would take care of that part. This one here, this one would be s over s squared plus 1. So s over s squared plus 1. This gives me cosine. Now, as that is just a 1, that's just going to be just simply cosine of t. So I can now add cosine of t. And that's the result of my initial value problem to find y as a function of t using the Laplace transform technique. Okay.